Hello, my name is Guy Moxey from Wolfspeed Power and welcome again to In the Studio on Location at PCIM. So now I'm joined with a gentleman who's got a very good eye for this industry. He's been doing a commentary around the changes, the trends from an engineer's perspective. I'm with Maurizio from AspenCore. Welcome and thank you for joining us.
Thanks for having me.
And it's good to be face to face once more again, isn't it?
Yeah.
So some life back in what hopes to be a very busy show.
Yeah, it's a long time. So it's PCIM is back in person.
It is. It's good. So during lockdown, you've run many successful panels, sessions, presentations. So this is kind of interesting because this is an interviewer being interviewed.
Yeah, exactly.
So we're switching positions here.
Yeah, exactly. So usually like editor for AspenCore, I did interviews with several speakers. So I did an interview with you too.
You have a couple of times, yes.
we replaced the rules.
So I've got this opportunity now to ask you what, from an interviewer's perspective, from an editor's perspective, in power electronics, because your background obviously is a doctorate in power electronics controls, I'm led to believe, so way more technical than I would ever go. But you obviously have a perspective, you speak to a lot of people, you see a lot of things. So in the last series of years, especially regarding wide bandgap, what's really been the thing that's been jumping out around power electronics, silicon carbide, GaN? There's a lot of good technology out there today.
Yeah. So wide bandgap is, the benefit of this technology is well known in industry. So, which is now turning to the question maybe of smart implementation for long-term cost performance advantages. So, but the question is, or the motivation for wide bandgap semiconductors, in my point of view, is because now we are changing the energy network. We are going towards a revolution. So the problem is climate change. One of the biggest issues of our generation is climate change. We need to reduce CO2 emissions.
Yeah.
How can we reduce these CO2 emissions? A lot of sectors are contributing, are producing CO2 emissions. So electricity production, manufacturing, transportation, for example. Transportation accounts for 20% more or less. So 3/4 comes from road transport.
Yes.
That means we need to replace the older traditional vehicles with a new one. And this new one is electric vehicles.
Absolutely.
But electric vehicles need more power, 20 times more than traditional vehicles. Traditional vehicles, internal combustion engine, ICE. And we need a lot of challenges for taking care about this power.
Yes.
So a lot of challenges. And the innovation in this field is wide bandgap semiconductor. Wide bandgap semiconductors, because gallium nitride and silicon carbide. Silicon carbide for sure is the main actors in electric vehicles, but also in energy. So
yes.
The main part of the market is EV and energy.
The energy to charge and drive the EV.
Yeah, exactly. So now we should talk about green energy for climate change, but also power electronics, energy efficiency.
Yeah, it's not just creating greener energy,
Exactly.
it's using the energy that's there, all being created much more efficiently.
Exactly.
Two ways of achieving the goal. And I think with certainly I'm biased towards silicon carbide, of course, but we go a long way in several of those end systems that you've already mentioned to make that difference. And you don't just speak with us, you speak with a lot of our colleagues, and which will be here this week. And there is some great advancements going on. Because, if we were having this conversation 8 years ago when I first joined Wolfspeed, actually, the question was, what is it? People had read it in academia, seen a little bit about it. Great advocates like John Palmer had been talking silicon carbide for many years, but the question is still, what is it?
So, silicon carbide, it is belongs to the wide bandgap family of material. So its physical bond is very strong. So and permit to have a high mechanical, chemical, and thermal stability.
Yeah.
And the high band gap, so the wide band gap and thermal stability, so offer high temperature operation.
Yes.
And that is important for electric vehicle, for example.
Yeah. Greater mobility, higher voltage breakdown.
Yeah. So I mean, silicon is reaching its limit in high power electronics. And if we are using silicon, we are losing efficiency. Imperfect semiconductor will translate in underperforming
Yes.
end system.
Yeah.
That means you are not replacing well electric vehicle, for example. So limiting their viability of electric vehicles, because the concept is, long range, battery, etc.
Correct. Yes.
So why silicon carbide? Or why wide band gap? So the element is band gap.
Yeah.
So band gap is, the amount minimum of energy of electrons to move from valence to conduction band.
Correct.
So this
yes,
is
that's right.
yeah, and
Physics lecture.
yes, the higher wide band gap, the more power
Yeah.
takes electrons
Absolutely. Yeah.
to move, to jump in this direction. So there is also, thermal energy in this case, because if the temperature increases,
Yes. If you
electrons
do work,
can
you expel energy.
Yeah, exactly.
Yes.
Can take energy
Yeah.
and move easily. So
Yeah.
for silicon, the temperature is 150 more or less. For wide band gap is much
Yes.
higher.
Yeah.
This is another element. So, silicon carbide will offer also, thanks to the features, less losses, and more switching speed.
Yes.
So, offer higher efficiency, and this allow, lower energy losses and reverse charge.
Yeah.
So another point that is important for high power is the drift region resistance. This is lower in silicon carbide. This offer high voltage devices application.
Basically, we get more amps for smaller chip and greater
exactly,
blocking voltage.
Exactly.
In
Power
applications
density.
terms, yeah, exactly.
Exactly.
And even over the last 4 years or even 2 years, and under lockdown situations, you've seen the technology within silicon carbide or other wide band gaps. But let's stay with silicon carbide just for the time being, because I'm obviously sitting in front of a purple screen. But you've seen, even in the last couple of years, tremendous leaps forward in product portfolio, packaging especially. It's wonderful to have a great chip, but if you're not putting it in the right package, you're kind of holding it back. And I think that's triggered, that's triggered the enablement into, you mentioned EVs at the start of the conversation, range, cost, power density, and the effects on the system, smaller batteries for the same range, or obviously same size batteries for extended range. I think the recent Lucid model that's come out is I'm trying to remember now, I should have looked it up, 500 odd miles per charge on the extended range. So it's getting to be a tremendous way forward. And you watch this, you put the commentary around this. So we talked about EVs, but what about the energy space? Renewables and...
electric vehicles for me is a crucial driver for renewable energies.
Yes.
Because when we talk electric vehicles, we, in particular, as you said, range, but also charging stations. Maybe now we have a lack in terms of charging station. DC charging station, just to charge faster.
Correct.
Faster charge.
Yes.
Just to charge faster. Because, in terms of electric vehicle, we can also have problem in terms of social and cultural. Because we are changing our life.
Yes.
So this changing is not only technology, it's also in our mind.
It is, it's a mental shift.
Yeah.
That's right, yeah.
And in terms of energy, so in my opinion, so for example, in my house, I'm using solar energy.
Okay.
I replaced my car with hybrid, just hybrid. The next step is electric vehicle. But the future is solar for me.
Do you have energy storage?
Yes,
Excellent.
7 kilowatt.
7 kilowatt, okay.
Yes. Yes, lithium battery.
So you have your own energy island in your house,
Yes,
basically.
yes, exactly.
Fantastic. That's incredible.
Yes, this is, this is the first step that each of us should do.
Yeah, if every domestic home, where possible, could replicate what you've done, Maurizio, it would be incredible. Because you must be energy neutral from the grid, basically.
Exactly.
I know you live in Italy, has a fair degree of sunshine, you know.
So we have a lot of sun, photons.
Exactly. So you generate a lot of things. You're storing it in your 7 kilowatt hour battery. So.
Yeah, because the problem is during the night. So during the day, there is no problem. So my solar photovoltaic, solar structure, solar plant, it's about 3 kilowatt. So I guess that during a sunny day, you can reach 2.5, more or less.
Yes.
And if you are not using all the power, maybe you are using one, the other 1 kilowatt is using to charge the battery.
Yes.
And you can use the battery for the night, during the night. So, energy storage is also a key element, factor for the renewable energy.
Yes.
Because the problem is during the night. In this case, you don't have energy, so there is no sun. This is the nature.
That's your battery. But
yeah,
it's interesting. You meant the solar system. So it's probably a small string system. The boost stage, the MPPT is
yes,
probably enabled with silicon carbide. Has been for quite a while.
I totally agree in this case.
Yeah, activity moving into the inverter stage. Obviously, charging the DC to DC, charging the battery. It would be an incredible place for silicon carbide at 3 or 4 times the switching frequency of silicon, reduce the size of the inductors. And then of course, when you do go to a BEV, not a hybrid, then obviously you've got the onboard charge.
You can charge.
And then of course the powertrain itself.
Yeah, so maximum power point tracking, MPPT.
Yes.
So this is an important element for the solar energy because so now with the IGBT, I guess, so correct me in the case, you can reach 96% of efficiency. But with silicon carbide, you can increase so until 99%.
You're getting up to,
and this is important.
In the 99%.
Yeah, more or less.
You mentioned a hybrid car. What's happened, and we've seen the transition in the industry from an all silicon boost system to a hybrid boost system with IGBT and silicon carbide diodes, and then more recently, the last couple of design cycles, all silicon carbide. So each time you go from 96 to 97.5, now to 99. And you're not going to get much better than 99%. Nothing's perfect. And when the solar panels are at best 25% efficient, typically,
more or less.
You can't afford to lose any drops of electricity at all.
Yeah. So this is the goal of silicon carbide.
Correct. Yes.
So just to also 1 electron is better.
Every electron. Yeah.
Yes, every electron.
Changing the world every electron at a time.
Yeah, this is. You need to take care all electrons that are around.
You do. You have to give them a big hug.
Yeah, and this is efficient, exactly.
So, obviously, on the vehicle, e-mobility in all shapes and sizes, from cars to buses to jet skis, and then charging of, creating and storing the energy. What do you think you're going to be seeing in the next 5 years for silicon carbide? That's all happened in the last 5 to 10 years. So we're now pivoting and looking forward over the next, let's say a next 5-year time span. Are we going to see just a lot more of the same applications, or are we going to see some new applications coming in as well for silicon carbide?
I guess that silicon carbide will be the best application in inverter onboard charger for EV, and we will continue to see a lot of this application for silicon carbide and also for energy. The market is automotive and energy trends, solar, energy storage, and so on. Maybe we need to reduce the cost. So the big cost of silicon carbide is in the substrate.
Correct. Yes.
Because it's not easy. So you know better than
we have some experience in that, and obviously what's behind us gives you an indication of where things are moving. 200 millimeter economy of scale with super fabs. So all of that is going to quickly come into the cost effectiveness and help towards the cost effectiveness, but it will always be a more expensive material to make than silicon. Just the sheer, that's correct, that substrate. But amps per wafer is 10x, probably more actually, of what you get from silicon. So, and then at a system level, if IGBT is switching at 20 kilohertz and we're switching at 70 kilohertz, those boost inductors in your midpoint tracker go from this size down to this
magnetic
size.
components.
So you've got to look at it holistically at a system, and this is why we're seeing silicon carbide really being. It's not the technology for tomorrow; it's the technology today.
It's not immediate. But yes, there is the future. So the problem is also in the all stages for the manufacturing of silicon carbide. So how many unusable wafer, unusable die after the epitaxy? This is a problem.
It's process, it's yields, but I've seen a huge difference in the last 8 years, and we continue to march forward, and it's a multi-decade opportunity. Your contribution of observing and studying and informing and communicating is tremendous. And you do it from an engineering perspective. So, you've carried us through the last 2 years of COVID by keeping us informed. So, just want to say thank you for that. And, hopefully...
So this is my passion. I like to write.
Exactly.
I like writing.
Exactly. Well, carry on. Please carry on.
Thank you.
I hope you have a wonderful show. It's looking quite brisk. I'm looking around. It's getting busy. So I'll let you go. Enjoy the next 3 days. And thank you very much.
Thank you. Thank you, guys.
For being here, Maurizio. Thank you.
Bye.
Goodbye.